In this video, I will be presenting a new photometry module that has been added to the Tycho software. This was the result of a request by another user of the software, and I thought that it would be interesting to go ahead and add such a feature. This is the result of 2 months of effort, and I started basically from scratch. Everything here is all new, and all the functionality has been added into the software. So what you're looking at today is now version 6 of the Tycho software. This has the ability now to generate raw plot and phase plot graphs. You can perform Fourier analysis and determine the rotation period of the asteroid, as well as the ability to adjust period and perform phase shift. And once orbital data has been attached to the photometry set, you can then have the program compute absolute magnitude. And once you've generated your measurements, you would like the ability to share them with others. So it has the ability to import and export out-def formatted files. And finally, there's also a new aperture setting tool, which allows you to specify the area under which the asteroid would be measured. So let's go ahead and take a look at a demonstration. Okay, so in this demonstration, I would like to cover 3 different asteroids. This will be done in increasing order of difficulty. Difficulty in this context can mean one of 2 things. One, it could mean that the asteroid has a small amplitude, in which case the photometry measurements have to be fairly precise in order to accurately determine its rotation period. Or it could simply mean that there are a lot of measurements to be taken, a lot of photometry sets to work with. And so as you can see, I've listed 3 different asteroids here. The first one is 771 Libera, and the purpose behind this one is to serve as a sort of benchmark. In other words, we want to validate that the photometry measurements generated by Tycho are on par with those generated by another well-known photometry tool, in this example, MPO Canopus. So let's go ahead and get started. Okay, so let's go ahead and take a look at the data for 771 Libera. As you can see, there are 2 different nights of data available here, September 18 and September 22nd, and this is in fact the exact same data set provided with the MPO Canopus package. It is available to the end user as an example data set to experiment with, and it serves as an excellent way to evaluate and compare when both programs have access to the exact same data. So let's go ahead and take a look at the images of the first night. And as you can see, the images are not yet aligned, and the background level is not yet consistent from one frame to the next. So that's the very first step, is to align and normalize the images, and then you can proceed with the next step, which is to then generate the photometry measurements. So let's go ahead and perform the first step. Okay, so the first item here is Express Mode, and so you go to the Action menu, choose Express Mode, and here you specify the operations that you want to perform on a set of images. So as I mentioned earlier, we want to perform alignment. We also want to perform normalization. And a third item here is plate solving. So we want to be able to convert from pixel coordinates to right ascension and declination. So once you've identified the operations that you want to perform on the image data, the next thing you can do, again, is to take it a step further. And batch mode allows you to perform those operations on multiple sets of data. So if we add directories, we can specify the first night followed by the second night. However many nights of data you have, you can list them here. And finally, the last thing you want to do is just verify the settings. So the automatic runtime module is used by the batch processor. So in this case, we do want to perform express calibration. And so as you can see here, these are the familiar options that we have. And so that's already configured properly. You just want to make sure that it is checked to be enabled. And because we are performing photometry of a known object, we do not need to run the tracker. So if it is checked, leave it unchecked. And finally, then I'm going to click OK. And then we can click Begin to start the processing. Okay, so as you can see, it has started the alignment routine, and in this case it has started the registrar program to perform the alignment. I like to use registrar just because it's able to handle meridian flips, distortion, image artifacts and so forth. It does a really great job at aligning images. But you could also use another tool. PixInsight works great for aligning as well. In any case, as you can see, it's already finished alignment, normalization, and now it has just finished plate solving. And now it has moved on to the second set of images. So it's pretty quick, although of course there are only 60 images in that first set and 50 in the second. But as you work on more complex and more involved data sets, you begin to appreciate that the software is able to automate the entire reduction process. And so we'll go ahead and give it a moment here, and it will finish up. So it has just now finished processing both sets of data. Okay, so at this point we're just about ready to start generating the photometry measurements. So what we want to do is go ahead and open up the processed output of the first night. So this is the result of processing night 1. And when we open up these images, if we wanted to, we could go ahead and examine them to make sure that they are aligned and have consistent background level. And so as you can see, this is the expected result of aligning the images, and you can pretty easily see the asteroid right there. So what we want to do at this point is go ahead and attach orbital elements of the asteroid to our data set. So to do this, we use the Find Orb software. This is developed by Bill Gray, and it's a wonderful tool. It works great, and I've made just a few small modifications to it so that it interfaces more easily with the Tycho software. So if you're not familiar with it, Find Orb, you can configure it, and I have more instructions on this in the user guide, but you simply specify the path to the software, and then Tycho does the rest. So in this example, what we want to do is download observations of this asteroid. So again, this is 771 Libera, and so when we click OK, it's going to download these observations, and these are observations that have been taken of the asteroid since its discovery. So this allows the Find Orb software to compute the orbit and so forth that we can then use as a reference for determining absolute magnitude and so forth. So we give it a moment, and now Find Orb has computed the orbit, and so we just go ahead and leave Find Orb running in the background. So this is kind of different in version 6. The previous versions would have you click a button and return ephemeris, but the issue with that is that when you're working with multiple photometry sets, you don't want to have to load up Find Orb each time. Instead, it would be nice to have it running in the background with the same object information. Now, before you can return ephemeris information to the data set, you need to make sure that the observatory information is configured properly. This is the information of the observatory that acquired the images. So in this example, this would be the observatory of Brian Warner, who collected these images. So we'll go ahead and specify that information here. MPC code is 716, and so what we can do is just simply click this button here, and it's going to populate these fields, the latitude, longitude, and height, and so forth. And don't really need to specify telescope info for this example, and we're going to say, data obs refers to beginning of exposure. That's usually standard. And so as you can see, there's now another observatory that we can select and choose from. This is a new feature in version 6, is that we can manage multiple configurations of different observatories. So now that we've done that, now that we've specified the active observatory that collected these images, we can now proceed to apply ephemeris information to the data set. So I'm back at the image manager, and I'm going to say ephemeris attached to data set, and it's going to prompt me for the instance of Find Orb to use. So again, we've already opened one up a little while ago, and it's working with our asteroid here, 771. And so I'm going to click OK, and as you can see, we now have the ephemeris information populated in these columns. So it tells us the right ascension, declination, expected magnitude, speed, position angle, and so forth for every single image. It also tells us whether or not the object is expected to be in the field of view for each image, and so forth. So once we've done that, now we can go back to the image viewer, and we can say, let's create a stack according to ephemeris. Now you could go to the top menu here and choose that option, or you could right click and say create stack ephemeris. So once you've done that, you'll now see a stack that has the stars as streaks, and the asteroid itself is now a singular object. So what we want to go ahead and do at this point is create a track so that it can generate observations that follow that object. So a few more windows pop up, that's fine. And so you get this track positions window. Normally when you create a track from ephemeris, it's not 100% accurate. In this example, you can see as you scroll through the images, it doesn't quite center on the object and so forth. That's not a big deal. What we can do is we can actually create a marker, so create marker 1, and then we go to the very last image and create marker 2. So what we're effectively doing here is we're telling the program this is the center of the object from the start to the stop image, and now we're going to create a new track from markers. So now we have a second track here that is a bit more precise, and when you follow the object in this fashion, you can see that it is centered much more correctly. So again, the ephemeris information gives you a good starting point, but sometimes you might need to make a slight improvement to it. So now that we have a track, let's go ahead and load up the star catalog, and now we can verify the track. This gives us a brief animation here so you can see it. And what we want to do now is we're now in photometry mode. So this is a new feature in version 6. It used to be that you could only create 3 observations, and generally that's all you want to do when you're just doing astrometry. In other words, when you're sending position information of an asteroid to the Minor Planet Center, they generally don't want hundreds of observations each night. So when you're just doing regular astrometry, that's normally what you want to do, especially when you're dealing with a faint object where you need to use stacks of images to get a better signal-to-noise ratio. In this example, we're going to choose photometry mode, and this allows us to generate observations however many we want. By default, it's going to choose the exact same number of observations as there are images. In other words, it will create 1 observation for each image. So now that we've made our selection, we can click Add Observations, and now it prompts us for a designation of this object. So if we want to, we can go ahead and populate that now. So 771 Libera, and then now it's going to create those observations. So pretty quick, and as you can see here, as I scroll through the list of observations, you can see it follows the object quite well. The green crosshairs represent the centroid, and so at this point we now have a good starting point for our photometry measurements. So let's go ahead and take a look at that. Now, as you might expect, the photometry measurements will be derived from these observations. So what you want to do is go ahead and select all of the observations that you want to use for photometry. In this example, I'm going to select all of the observations. So once you have made your selection, then you right-click and choose Copy to Photometry. And in this example, we are going to create a new set of data. So I would choose this option. And once you have done that, then you'll notice 2 windows appear. The first of which is the photometry set window. This shows all of the sets of data. In this case, we have only 1 so far. The other window is that of the photometry measurements. So these are all the measurements associated with that particular photometry set. At this point, it's a good idea to go ahead and save the work in progress. So you can go to Save to Repository and give it a name. And because we do have data points on an object, we could go ahead and create a graph. So I'm going to do that now. And as you can see, this is a decent starting point. This is a basic light curve of the data points that we have generated so far. So this is what is called a raw plot of the data. And we can go ahead and give this a title. And at this point, we might also be curious to know how does this compare with the measurements taken with another photometry tool. So let's go ahead and take a look at that. Okay, so as you can see, this is the plot generated with the MPO program. As you can see, the data points look quite similar from one program to the next, and that should instill confidence that both programs are able to generate similar photometry measurements when they have the same data. And so that's the whole purpose of this exercise. This very first asteroid example here is to indeed validate that the new photometry module in Tycho is able to generate accurate photometry measurements. Now the next step then is to ensure that both programs compute similar, if not identical, rotation period values when given the same search parameters. Now, of course, in order to do that, we need the second night of data. But before we do that, I'd also like to touch on a couple of other items here. So there are different ways to plot this data. These are other options available to you. So some of you might be familiar with these other ways to present the data. So for example, this classic view, this is a way to render the data in a fashion that is one that others may be accustomed to seeing in the Minor Planet Bulletin. You also have the option of showing, for example, a legend and so forth. So this gives you a way to render the data, again, in a format that others are accustomed to seeing. So these are other options available. You can change, for example, the size of the plots and so forth. And so, of course, the vertical bars here represent magnitude and certainty. So at this point, we can go ahead and proceed with generating the measurements of the second night, and that will allow us to perform period analysis. Okay, so I went ahead and generated photometry measurements of the second night. So I'm going to load up photometry analysis here, and as you can see, when I load from repository, I now have two sets of data. So this again gives us another window here. So with these 2 nights of data, we can begin to determine rotation period. But before we do that, it's good to go ahead and populate these columns here. I went ahead and did it for the first night of data, but I'll go ahead and do it for the second as well. So to do that, we simply right-click and say Apply Object Data, and we could do this for both at the same time. So go ahead and do that. This works similar to applying ephemeris information. So you simply select the instance of FindOrb that has the orbit determined for that object. So I've been leaving it in the background for about an hour and a half now, and it's just been sitting there waiting for Tycho to give it a request. So I'm going to click OK, and as you can see, these columns are now populated, and we now also have more columns populated for the measurements as well. So we now have light time correction, we have the absolute magnitude and so forth that we can use to determine period analysis. So if we want to, we can go back to plotting the light curve. And now, as you can see, we have our first night here and our second night here as well. And you'll notice that they're offset a little bit, and that's just because of the elapsed time that has occurred. So what we want to do is normalize the magnitude information, and what we can do there is simply say, let's use absolute magnitude as opposed to measured magnitude. So when we do this, you'll notice that they now line up more correctly, and this is good to have for the period analysis routine. So you can also choose to say, yes, let's go ahead and use light time correction. So now you see this is set here. That makes more of a difference if it's a really close object and so forth. But anyway, let's go ahead and run the period search tool. So all I have to do here is go to period, find period, and it gives us this window here. And so now you have your parameters, your settings to use for the search. So it's important to make sure that your start and stop time is wide enough to include what the actual period of the asteroid is. So I specify in this case 0.5 hours to 12 hours, and in this example I'm just going to choose 100 steps just to start off with, and we're going to use the 4th order here, and then we'll keep all the time units in hours, and we could do seconds, minutes, or so forth if we wanted to, but we'll keep it in a time unit of hours. And then number of threads here, this is just simply how many CPU threads do you want to use that can help expedite the search. So I'm going to click Find Period using these parameters, and it has found the period here. Let's see, so it gives us a few more windows to look at. So it has identified a period of 5.89 hours, plus or minus 0.115 hours, and that's plus or minus is dependent upon the number of steps. So if you increase that to 1,000 steps, then of course the step size also reflects that as well. So the period search window indicates all the relevant periods that it found, sorted by root mean square. And so again, 5.89 hours is the first period, the best one that it found. And you also have a plot of the period spectrum, and this is by default in log scale, but you can choose linear if you want to. So as you can see here, this is the 5.89, and then over here we have the 6.72 or what have you. So you can actually click on different periods, and as you do that, it will change the phase plot here. So we are now looking at the phase plot as opposed to the raw plot of the data. And so if we want to go back to the raw plot, we can always change it to that. So we always have the option of going back from one to the other. And we can also adjust the phase shift. So if we want to adjust that here, we can do so using the slider. So that makes it easy. Alternatively, we could also apply some changes to the period in this fashion here. So as you can see, when we make minor adjustments to the period, the graph no longer looks like a good fit of the data. In other words, so just these minor changes to the period are enough to make the phase plot look strange. So 5.89 appears to be a good fit. And so let's go ahead and see if we get a similar result with the MPO Canopus program. Okay, so we are now back at the MPO Canopus program, and again the point here is to determine whether or not it can yield the same or similar rotation period when given identical search parameters. So we start off by exiting out of the raw plot mode, and we enter into the Fourier Analysis mode of operation. And when I click the Find button, it is going to prompt for what data sets to use. So we want to use the same data sets that we've been working on so far. So that would be September 18 and September 22nd. So if I include both of those here, and click OK, so it looks like it comes back with a period of 6.25. Now that's a bit different than what we had over here. We had 5.89 over here, so that's a bit of a difference. Now the amplitude looks to be quite similar. We have 0.48 over here and 0.47 over here, but certainly the period is a bit different now. That might not be unexpected given that the step size is 0.115, but we might be curious to know what should the actual rotation period of the asteroid be. So we can actually find that out if we go to the Photometry Analysis module. There's actually an option to search the AlcDepth database. So this database is actually comprised of the raw data for a select number of asteroids, and it just so happens that our asteroid here is among those that are included in this database. So if we do a search on it, it will hopefully come back with the desired result here. So we give it a moment, and as you see here, we have one result returned, and there are two light curves available on this object, and it just so happens that they are in fact the same ones that we've been working with. So September 18 and September 22nd. Now when I import the object, two things happen. One of which is it gives us details on this object, and it also imports that raw data into the photometry module itself. So in other words, we'll actually be able to plot the data from the AlcDepth database and process it and so forth. So because we have imported that data, we need to go ahead and apply the object data once again so that it is up to date, and then again we can graph it using absolute magnitude to normalize the magnitude, and might as well use light time correction as well. And now again, back over here we have object details. In other words, we can determine some information about this asteroid, and so in the object summary it tells us that the period is supposed to be 5.89, and this is determined from a number of references here. And so one person says 5.93, another says 5.89, 5.886, 592, and so forth. So there's this tendency to agree that somewhere around 5.89 is in fact the rotation period of the asteroid. So that should instill some confidence that indeed Tycho is able to compute the correct rotation period of the asteroid, even using measurements computed from within itself. In other words, we reduce the data within Tycho, and we generate measurements from Tycho, and Tycho is able to compute that period. So now let's go back to MPO Canopus, and if we try probably a smaller step size or so, then hopefully we can also get a similar result. So if we try a 0.05, that will increase the granularity, and of course when we do that we also need to increase the number of steps. So if I try 200 steps here, of course you want to make sure that you still include the actual period within that search range. So if we go back to period search, so 200 steps, and we want 0.05 as the step size. So I do a period search a bit differently in that I don't ask the user what the step size should be. I simply ask them what range they want to search and how many steps do they want. That way they don't have to do arithmetic in their head as to what the stop value will be. But in any case, it looks like 10.5 will be the resulting stop value here with these parameters, and that means that 5.89 will still be included in this combination of step size and number of steps. So when we click find, then we'll see what happens, and it looks like 6.7 is returned. So again, we still don't have the desired result, but let's try another reduction in step size and increase number of steps. And okay, so it is increasing the precision, but we still don't have a desired period. So 6.7 again is still not what it should be, but I will try another step size. Let's go to 0.01 and then 800 steps. So if I have 800 steps, and 0.01 should be the step size there. So it looks like that should be 8.5. So again, 5.89 will be included in that search range. So I click find, and okay, now we have 5.87. So 5.87, that's pretty close to the 5.89. And so indeed, both programs are able to compute the rotation period of the asteroid, and just a matter of sometimes you have to play with the search parameters to get there. So if I put these parameters into the other program, so we have 800 and again 0.01. Let me make sure. So I click find period, and so again it still agrees that 5.89 is the period of the asteroid. So again, we should have now confidence that Tycho is able to not only generate accurate photometry measurements, but also compute the rotation period as expected. And also, just for comparison, here's what period spectrum looks like, and then the same from NPO. So this is log scale, so both programs produce a similar period spectrum. So again, that's also a good result there. And so hopefully now we have some validation that this new feature in Tycho is actually something useful because it is actually able to generate accurate results. And so this is the again the first asteroid. This is a fairly straightforward one. So now let's go ahead and take a look at another one.